Welcome to exciting episode 2 in Game of Magnets. In this episode I will attempt to do at least half as well as Mary did in the first episode at clarifying the way electricity and magnetism work. But first a warning. At some point in this talk I'm going to make a statement something like the B field of this magnetic dipole is about half a Tesla. Is there any chance you understand any of those words? I mean, there's a fair chance I don't understand. There's a lot going on there. One of the big problems I think that we as introductory teachers have is that we as a class, meaning teachers and students, jump past these introductory terms quickly to try to get into what seems to be important stuff. And so both the teachers and the students go zipping through those introductory points without getting them clear. And we need them clear in order to understand what follows. And so let's go back to my statement and start with the word field. From the physics standpoint, a field is a region of space to which each point can be assigned a specific measurable value. As a quick and easy to understand example, let's look at a weather map. In a weather map, we have a two-dimensional region of space, and at each point on that map, we can easily measure a temperature and put it down on the map. The map that we have here shows the Pacific Ocean with Asia on the left, North America on the right, and temperatures running all the way across it. It's also kind of a neat look at the range over which all of us are now occupying. The little hand over there at the far end of North America is over Philadelphia, which is where we're presenting the program from. But we go all the way over to the left, well into China. Any of you folks in South America or Europe, I apologize for not fitting you in here. Next time we'll do that. But as you can see, we could assign temperatures everywhere. Those temperatures are simple numbers. They're quantities. They're scalar. And the upshot is that this temperature field is a scalar field. We've assigned a single number to each point in this region of space that we're talking about. Also on this map are these little streamer lines. They indicate wind, and we want two pieces of information about wind. We want to know its magnitude, but we also want to know its direction. Wind is a vector, and we do that now by putting a streamer or a line or an arrow at each region of space, the length of which corresponds to the magnitude, the direction of which corresponds to the direction. And so you can see these little streamers on the map showing us both how strong and in what direction the winds are blowing. Where does this fit in to physics? Well, Mary was talking about electricity and charge and magnetism, and both of those quantities generate measurable values in space. There is an electric field, and we can mark off regions of space in which we can specify how much force each coulomb of charge will receive. Clearly we can put a direction on it. And in the same way we can mark off a magnetic field. So let's talk about that, because that is part of the vocabulary we need for what we're going to talk about in this lecture. And so behind me we have a magnetic field. And it already gets us to another term in that sentence I warned you about, dipole. Please notice that unlike the electric charge, where we might have just put a positive in here, we've got a north and a south. And in the case of electric fields, if I put a positive here, the field lines would radiate out to infinity. With a dipole, we have closed loops. We have lines that radiate out from one pole and come around to the other. The size of those lines indicates how strongly that magnetic effect will be felt. The arrows, and this is important, are in the direction of the magnetic field. And the agreed upon direction of a magnetic field is the direction that the north end of a compass points. And so we know opposite poles attract, like poles repel. And so the north end of a compass is going to point away from the north end of the magnet. And so this field points away, and if we put a compass needle in this area, the north end of that compass would point away from here, and obviously the south side of that compass would point towards the north field. As we move around in space, that compass needle now is going to be acting in such a way that its north end is attracted to this south pole. The south end is attracted here, and the compass needle is going to rotate around, changing its direction, and it comes in here. Neat picture, interesting story. Does it work that way? Well, let's take a look. We have here a nice bar magnet. We've put red tape on the north pole, black tape on the south pole. Kind of a standard approach to indicating magnetic poles. If I take this magnet and place it on the glass, and I can do that by putting magnets behind it, we can actually get our north-south magnet in space lined up with the field that we had imagined around it. And so, is this all just an abstraction? Well, I've got a compass here. I've got a magnet that's free to turn. And let's put it into place here, and we notice that its south pole lines up with the north pole. The north end points away. But as I bring it around in space, notice that it changes direction until the north end points at the south end of the magnet that is causing the field. And so, in fact, our compass needle really does act the way our field lines tell us that it should. So, is this just an interesting video game? Well, no, it's not. The idea of field was initiated by Michael Faraday. And Michael Faraday used this to solve a problem that had eluded even Isaac Newton. When Newton talked about gravity, he told us that two massive objects would attract one another by gravity. Of course, he suggested those objects could be things like the sun and the planet Earth. And it was pretty easy to say, well, how do they know each other is there? And Newton really couldn't come up with a mechanism. He could tell you how strong those forces were, but he couldn't come up with any explanation for what mechanism they interacted through. Maxwell proposed a middleman of sorts. Maxwell suggested that what we see here in the behavior of this magnet, and of course it would transfer to Newton's situation with masses, is that the compass needle is not reacting to the magnet. The compass needle is reacting to the field. And so the field is what happens when the magnet shows up in space. So this magnet changes the properties of space. This compass feels the properties of space. And so the field gives us the stepping stone we need in order to get the influence of one object to show up in the presence of another one at a distance. Do we need this? Well, the place where this is really helpful, and one of the real tests of scientific theory, is not only does it help us with what we know, but in this case it actually lets us expand from our starting point into an arena that we didn't really know. And so the thought that this field could exist, that space could have this property, which if we cover this magnet up, okay, the space still has the property even if we can't see the magnet. We are going to discover that there are ways to produce magnetism that do not involve magnets. We're going to discover, and Mary pointed out, okay, actually I shouldn't use future, Mary showed us that if we have a coil of wire that we run electricity through, we get magnetic effects. There's not a north and a south end to this. But what we can now say is we create a magnetic field. And so the concept of field lets us generalize the statements that we make about magnets from the specific presence of a visible permanent magnet to a situation where other things produce magnetic behaviors. And in fact, there are several other things, and understanding them is critical to getting a full picture of electricity and magnetism. And so given that, the next thing that we clearly need to understand is how do we talk about this magnetic field? The first thing I want to do is bear down on the units of magnetic field. Because if we know the units of a given measurement, they almost tell us the formula that we're going to use that measurement in. So here we are at the most exciting part of this talk. That's right, the guest appearance from Mary. So these were the formulas that she talked about in her talk. And we're going to revisit them. You're right, you've seen them before. We're going to revisit them because we need to get a really clear understanding of what B is. And so we're going to take a look at those equations, and we're going to use them to figure out what B is. And then, once we understand the units of B, that will give us the ability to have an operational definition of magnetic field. And by operational definition, I mean we will have a process, an operation we can perform that will tell us what B is. And so that means we've got an unambiguous understanding of magnetic field. So let's have a look at those formulas. We put them up here on the screen. Mary's formulas relate to a situation where there's a wire. Here we've got a wire with a known length L, and there's a current in the wire that we know, a current I. And the wire is in a magnetic field B. In this diagram, the magnetic field goes into the board, and we indicate that by having circles with X's in them, which imply that the vector arrow for B is going away from you, the viewer, and you're seeing the tail of that vector with the tail fins visible. The result of that, based on the calculations as Mary explained them, is a sideways force on this wire. So let's go back to the formula. We realize that we understand that force is a push in newtons, current is measured in amps, length is measured in meters. The only thing we don't know is B. So let's move all the terms over to the left. So B is the subject of the equation. And we've got B equals F divided by current times length. That gives us an idea of units. Force is in newtons, current is in amps, length is in meters. And so B has the units of newtons per amp meter. Now, as with any of these derived physics units, if we're going to use them frequently, we'd like to get something a little easier to talk about. So we are going to define a newton per amp meter as a Tesla, named after the electrical engineer and scientist Nikola Tesla. And so now we've got that operational definition. What is the operation? If we want to know a magnetic field, we take a wire that's a meter long, we run an amp of current through it, and we put it in the magnetic field. We measure how much force that wire receives, and that is the magnetic field. That is the number of newtons per amp meter of force acting on it. So a magnetic field then is defined as the effect it can have on an electric current. What if it's a single charge Q? The formula looked like this as Mary showed it to us. We can once again make B the subject of the equation. We get F divided by charge Q in coulombs times meters per second in velocity. If we look at those units, velocity, of course, is a derived term. Let's put in the meters per second. And now we can associate the second with the charge. So we bring the S over, and we can now express this as F over charge per second times meters. Charge per second is nothing more than amps. And so we get the same outcome whether we're looking at a single charge or a current in a wire. Newtons per amp meter. When they first started studying magnetic field, they couldn't produce really large magnetic fields, and so they used a unit that was much smaller that worked well with small amounts of magnetism. That was named after Carl Friedrich Gauss. It was in fact so small that it takes 100,000 of those Gausses to equal 1 Tesla. So a Gauss is 100,000th of a Tesla. Do you ever use anything that small? Yes, you do, quite frequently. The Earth's magnetic field is pretty weak. It is the field, of course, that aligns a compass needle and points it north, and it is about 1/2 a Gauss. So we've now got a concrete understanding of what this magnetic field is. It's not just there's a field here. We know that it means that in this region of space, a current carrying wire is going to receive a force. Now that we understand what the words for magnetism mean, when we talk about a magnetic field, we've actually got a term that we can relate to the rest of our physics. Let's quickly revisit the demonstration that Mary showed us and remember how it works. And so Mary took a coil of wire. She had a steel rod that was really just a steel rod. It had no effect, it was not magnetized, had no effect on these washers. And she applied an electric current to the coil of wire wrapped around the rod. And we're going to do that visibly with this knife switch. And notice we have no magnetic effect here. As soon as we electrify the coil, it magnetizes the rod. When we get rid of the electricity, we lose the magnetism. So we have here what's called an electromagnet, and this, of course, was the experiment that caused scientists to realize the connection. And so now we're going to take a look at, the reason we looked at this is because it was the thing that motivated scientists to think that maybe if instead of using just a piece of steel, they took a magnetized rod and put it in there, maybe they'd get electricity in the wire. So we're going to take a look at that now on an apparatus that's a little bit bigger and easier to follow. So now that we have a good idea about the terminology of magnetism, it's time to move a step forward, to see if the opposite of the experiment we just looked at with using electricity to produce magnetism is possible. Is it conceivable that magnetism will produce electricity? And so we've got a coil of wire here, as we did in the past, but instead of putting just a piece of iron in there, we're putting a permanent magnet in. So the magnet goes in here. This experiment was done by many electrical scientists in the early 1800s, among them the British scientist Michael Faraday. We have a meter that measures millionths of an amp, a microammeter, and to protect that meter, standard practice is that you don't turn the meter on until everything's ready. You can monitor the meter, and you try to make sure you come in with the lowest amount of strength possible in case this thing produces enough power to damage the meter. So we've carefully included a switch here, so there's no expectation of electricity flowing until we move this lever. But now everything's ready, magnet, coil of wire, wires coming here, please note it's a center zero meter. With a center zero meter, it doesn't matter which way the electricity flows, the needle will move visibly. And so we will now close the knife switch and see what all those scientists in the early 1800s saw. Nothing. And so they would take this thing apart, they'd disconnect it, they'd take the pieces out, okay, and they would try many things. They would try stronger magnets, they would try bigger coils, they would try different orientations. They would continue to get nothing. In 1831, some combination of factors, maybe as simple as taking it apart in a different order, led Michael Faraday to see this happen. The needle moved. If you move this magnet while the connections are made, an electric surge happens and the needle moves. If we go back, we put the magnet in, we in fact see an electrical effect from the magnet. But what's surprising and unexpected is that it's unrelated to the presence of magnetism. What has to happen is the magnetism has to change. This is a revelation about both magnetism and physical behavior in general. The importance of a changing value is a new idea in the early 19th century. And so if we leave this sitting still in here, it reads as it had read up until this point in time. There appears to be no electricity. But as we move this, we get an electric effect. And so in fact, we can now say that an electric current produces magnetism. And now we can say that changing magnetism produces an electric current. But let's go one step further. Remember this whole thing about magnetic fields. Remember that we had proposed that these magnetic fields could be treated as freestanding properties of space. That they were created magnetically, but they were reacted to locally. And so this wire doesn't know whether there's a magnet here at all. It just knows there's a magnetic field. And so we've got a magnet here, but what this wire senses is a magnetic field. There are other ways to produce a magnetic field. In fact, we can produce a magnetic field with another coil of wire, which we're going to do. So we've got these coils now set up as we described. Please note there are no magnets present. This is the coil that we generated electricity by moving the magnet through. But now, instead of having a magnet, we just have another coil. Since we know the meter seems to be okay, we've switched our knife switch to controlling a 6-volt battery supply that runs current through the second coil. So what's going to exist in this coil isn't a magnet, it's going to be the magnetic field. It's going to be this thing that we have told you has a measurable property. It is newtons per amp meter, and it can exist in space as a single object, as something that we can measure and look for the effects of. And so does that really work? It sounded like a good idea. The math falls together, but do things work that way? And so we're going to close this switch and make a magnetic field. Our thought is that it was the changing magnetic field that made electricity. So this ought to happen in the absence of any other physical objects, if that idea is correct. So let's try. When I close that, the needle moves, not very much, but visibly. When I break it here, obviously when I connect it, we make a magnetic field. That would be similar to pushing a magnet into the coil. And when I disconnect, it's like taking it out. And in both cases, we saw electricity produced by a real magnet. And so it stands to reason that the magnetic field, if it behaves as it did when the magnet was moving, should produce this effect. Now the problem that we have here is that the magnetic field, in the absence of iron, is pretty dissipated. Iron focuses magnetic fields. What we've got here is a bar from a barbell. We're going to use it as an iron core, and we're going to put it in here. Now please note, it has no effect on the needle. There is no magnetism present in this, it's just a piece of iron. But what's going to happen is the magnetic field that we produce by running current through the right-hand coil is now going to be more concentrated in this inner region, and we are going to then see the effect of the changing magnetic field on the second coil. So let's see how effective this core has been. Well, now the needle moves tremendously because we have a bigger change in the magnetic field. And so when the magnetic field changes in one way, it goes up. When it changes in the other way, it goes down. We have to be attentive to the fact that these changes can happen 4 ways. Not just the fact that it rises or falls, but remember, magnets have poles. And so if we have a situation where the north end enters and we increase the magnetic field from the north pole, or we move it out and we decrease the magnetic field from the north pole. But the other situation would be that we increase the field from the south pole, or we decrease the field from the south pole. And so we need to be aware that those 4 descriptions exist. We're going to talk about them and see how they affect the production of electricity. So let's sum up what we know. Mary told us that when an electric current flows in a wire, it creates a magnetic field. We took that and said, all right, what about the reverse? And we discovered that a magnetic field can produce electricity if the magnetic field changes. Up till now, we haven't used the word induction, but let's bring it in here now. The fact that we can produce an electric effect from changing magnetism is called induction. It's a word that gets used in many applications, in everyday language and in technical usage as well. The common theme is probably that it means we produce an effect without a clear, direct linkage. So for instance, if we induce something about a person, we use a couple of observations to draw a general conclusion. This idea of induction is important in all areas of life, but we have to be careful with it. If we observe that 0 squared is 0 and 1 squared is 1, we might induce that the square function produces the same number you started with. Doesn't mean induction's bad. It means we have to be careful with it. We need multiple examples. Electrically, the induction process is also one that we don't see the direct connection. It's a surprise that changing the magnetism in a coil produces an electric effect. And so we didn't come in. A non-inductive way to get an electric current in a wire would be to hook up a battery. It's quite clear there's a direct connection there. In the case of the magnetism, there's not. So the use of the word makes sense. I was also careful not to use the term induction right away, because we all are in the habit of thinking that if we know the terminology, we understand the behavior. I think it's much more important to master the behavior and then find a name for it. And I'm hoping that we're moving along that path. But at this point, I think it's important to get used to that word, induction. And it's also important now to get used to the nuts and bolts of the behavior. On the screen here, you can see that we've illustrated what we've already demonstrated. If we have a coil of wire and we move a magnet into that wire, we increase the amount of magnetism within the loop, and that produces an electric flow around the loop. We now need to come to grips with the specifics of how do we measure and predict the behavior. And so we are going to postulate that a magnetic field can be illustrated with a series of lines. Those lines are called flux lines, and they emanate from the north end of the compass, And because we don't have monopoles, because we have to have magnets with two poles, those lines circulate around and close off at the south pole. These flux lines radiating out in space are what enter this ring, and we could say that the induced electric effect, E, is proportional to the rate at which we change these lines. And as we said, the name for the lines is flux lines. We've written it here. You want to get the spelling right. You don't want to make embarrassing mistakes here. The symbol for flux is the Greek letter phi. Some people call it phi. I'm an advocate of calling it phi, but a number of folks defy my description. In any case, this series of lines coming out of the end of the magnet is the most fundamental measure of the magnetism. We, however, up to this point, have talked about Tesla. And what's Tesla relative to this? So if you notice, the B field is number of flux lines per area. What does that mean? Well, this magnet doesn't show its flux lines anywhere near as well as this magnet. Look at that. You only get this stuff at major universities, okay, or at least in houses that have a couple of extra scrub brushes. And so we're going to suggest that from the north end of the magnet we have the positive emission of flux lines, and clearly if it's a north pole we'd expect it to be kind of Christmassy with the red indicator and the green flux lines, right? I'm sure that's the way it works. These lines go out in space, wrap around, and re-enter the magnet at the south pole. So we would call this a positive line pattern, and here the lines are going the other way. We would call that a negative line pattern. So we've now got an illustration of flux lines. If we want to measure a magnetic field, we take a field checker, okay, no expense spared, you can see my field checker. We come in here and measure a magnetic field. Now, did we catch all the flux lines? No, we didn't. You can still see there are green bristles that didn't get into my sensor. The sensor has got an area, and we could only measure the flux lines that went into that area. So consequently, when we measure magnetic field, we are measuring flux lines per area. To get all the flux lines, we would have to do what we did with light when we talked about that. If we want to measure all the light coming out of a light source, we would have to wrap the light in a great big sphere and count all the lines going through the sphere. And so in order to do such a thing, we say that the flux is equal to the magnetic field times the area. A simple rearrangement of that formula. But in the long run, because the whole magnet is going through the coil, all the flux lines go through the coil. And so our formula is going to be stated, change in total flux per time is proportional to the electric effect. And so let's imagine that we've got this. You know, one of the real issues with understanding electricity and magnetism is that it's invisible unless you've got really neat magnets like we do. It's three-dimensional, and there are all these right-hand rules. And so we got to visualize something we can't see in three spaces. Here I've drawn it in two, but that's limited. And with all these if you're writing something down, is your right hand available to figure this out? And it turns out there are a couple of places you just don't have enough right hands. And so we've solved that problem by picking up a couple of extra right hands. And so here we've got our circle. Let's imagine, just as on the board, we bring our magnetic field through it. In this instance, this change in flux over time, and you know, because we can put a sign on flux lines, that change can have a sign. And so as it comes in here, we're increasing the number of positive flux lines. So delta phi delta t would be positive. If I turn this around, these are flux lines heading towards the south pole of the magnet. So in fact, I am bringing in here lines that point the other way. So that would be a negative rate of change. If I start my observation with the magnet already through the coil, if I pull back on this, these are positive flux lines, but I am reducing the number. That would also give me a negative number. And in the same way, if I have my south pole through the coil and I pull it out, I am reducing the number of negative flux lines. Two negatives make a positive. If I reduce my debt, I'm actually improving my finances, right? If I reduce my negative magnetism, I've got a positive change. And so we've got to keep all of that in mind. So how does this work? Well, let's make a hypothesis and follow it through. So remember, this isn't necessarily the outcome. We're reasoning to an outcome. So let's assume that the right-hand rule works. Let's assume that we're bringing the north pole of a magnet into the coil and that this increasing flux line pattern produces a right-hand rule electric influence. The E field goes this way and the corresponding current goes that way. That means with the right hand that we are going to get a counterclockwise movement. From what Mary told you in her talk about magnetism, we know that if we've got the direction of an electric current, a right-hand rule comes in and lets us figure out what kind of magnetism it produces. And so if the current is going this way, here's my counterclockwise movement, my thumb goes that way, my fingers wrap this way. Now I can't do anything, but you know what? More right hands, that's right, okay? You got to get more right hands. And so let's put this right hand here in place, and what's this saying? This is saying that the current going this way is going to produce a field that wraps from the inside out. But the flux lines inside the coil are pointing towards you, viewing towards the camera. Well, that's the direction we were increasing flux lines in the first place. And remember, what did we say? We were suggesting that the change in magnetic field in this direction was producing a current in this direction. Is it possible that that's going to make a magnetism that produces more of that current, that produces more of that magnetism, that produces more of that current? We've solved the energy crisis. I'll bet it doesn't work that way. I'll bet there's a problem with that because there's no way we can continue to produce energy with no effort. In fact, it turns out that this hypothesis is wrong. So let's for a moment take these hands out of here and let's try the other hypothesis. And see, this is why it's cool to have spare right hands. All we have to do is turn that hand around. And what did I just do? I suggested that we now point our right thumb opposite to the direction of the change in magnetic flux. And so the flux is increasing towards the camera. We're pointing our thumb away from the camera. That would imply that the electric field and current that get induced are going to be clockwise. If that's the case, we bring in our original right-hand rule, and we put our thumb in the clockwise direction, which tells us that the magnetism we produce comes towards the camera outside the loop, where it doesn't matter. What matters is what's inside the loop. And it wraps around and goes the other way inside the loop. And so the magnet is increasing flux lines towards the camera. The current is fighting those flux lines by producing flux lines going the other way. What does that mean? It means that everything else we knew about physics works. It means that energy is conserved. It means that if I am making an electric current by moving a magnet in a coil, the coil is producing a magnetic field that pushes back on the magnet. I don't get the electric current without providing an effort. Force through distance is energy, mechanical energy being traded for electric energy. And so what we need to do with our equation, and this is important, pay attention as we add this, we need to put, taking away the proportion sign, we're going to put a minus sign in there, and then we get to say equal. And so our induction law, our induction formula is that induced electric field is negative the time rate of change of magnetic flux. So that minus sign looks trivial in your book. It might look a little confusing. It is one of the cornerstones of physics. We can't get something for nothing. It is also the doorway to what's called Lenz's law. L-E-N-Z apostrophe S. Lenz was the physicist who studied this. And according to Lenz's law, and it kind of says the same thing in words, if I induce an electric current by putting a magnet through a coil, the induced current will create a field opposite to the field that caused it. So in goes the magnet, we're producing a current that produces a magnetic field that opposes it. In more technical terms, the electric current is in a direction to fight the change in the flux. So if I try to increase the flux, I'm going to get a current that tries to decrease the flux. If I'm going to decrease the flux, I get a current that tries to increase the flux. Can we demonstrate that? Well, I could drop this magnet through this coil. And for a brief moment, I would increase, if I drop the North Pole first, I would increase the flux in the field, or in the coil. The coil would push back, and there'd be a brief pushback on this magnet as it went through. It would happen quickly enough that it wouldn't be visually dramatic. It would be nice if I could stack up coils and get a whole pile of them and drop this through so the effect was continuous. Then that would fight back all the way down, and the ability of the magnet to move would be significantly impeded. As you can see, we've created some clever apparatus for this demonstration, and I've created another clever one. I've taken an infinite number of little copper rings and assembled them into this very fantastic, highly technical device. When I Googled it, I discovered that somebody else had also discovered it. Okay, so this is a piece of copper pipe. Now, what's it going to do for me? It really can be visualized as a stack of conducting rings. And I've got my magnet here, and if I drop it through, that first ring will get an induced current that's going to fight this change in magnetism. It pushes back. Well, what's pushing the magnet? Gravity. If this falls really fast, the pushback would be more than this object's weight, right? Which would mean it would go back up. Is it going to do that? No. Because as soon as it comes to a halt, there's no change at all. Delta phi over delta t is 0. There's no current. There's no pushback, so it falls. As it falls, it makes some current. It pushes back. It's going to eventually reach an equilibrium with gravity. It's going to fall at a rate where the induced magnetic field pushes back with a force that matches gravity. Does that mean it stops? I hope you don't think that. If force is 0, acceleration stops, not velocity. And so it will move at a constant velocity without changing its speed. But that velocity is going to be substantially slowed down. We call that a terminal velocity. It is the final speed that it can go after all the forces adjust. So if there's any question about whether I'm playing games with my clever new invention, the copper pipe, let's take a pencil and drop it through the pipe. And you will note, here goes the pencil, okay, comes through right away. There's no obstruction in the pipe. So let's put this in view of the camera and drop the magnet in, and notice nothing, even an old man's got good enough reflexes to get down here and catch this magnet when it's that slow. Seriously. The stronger the magnetic field, of course, the bigger the effect. And I didn't choose copper by accident. Copper is the second best conducting metal. The first best, why didn't I use the first best? It's silver, okay? This would cost a bit in silver. In copper, it's not cheap, but it works really nicely. And so we put this in. Let's try it again if you missed it. There it goes. It's sliding down, sliding down, sliding down. It takes quite a while. And we should point out that the induced electric field is always the same. What's different? The amount of current. The current depends on the resistance of the ring. So if I did this in some metal that didn't conduct as well as copper, it wouldn't work as well, because remember, the induced field is an electric field, but the thing that makes the magnetism is the current. So I get the effect if there's lots of current caused by that voltage. If I cool this down, resistance goes down with temperature. If I cool this down, the resistance goes down, the current goes up, the opposing magnetism goes up, and this falls even slower. So it's kind of interesting to start stitching together all of the features of the way electricity and magnetism behave. So our final statement then is that the law of induction is that the induced electric potential is equal to negative the rate of change of magnetic flux per time. That's the contribution that James Clerk Maxwell made. It's the last of Maxwell's equations, and they're called Maxwell's equations because he summed them up really nicely. But the induction law is, well, actually the discovery we said was made by Faraday. The mathematics was done by Maxwell. And so we've now got this sense of electric induction. One last point. Maxwell used this to figure out what was happening with light waves. Light waves are an electric field changing in space in typically a sinusoidal fashion. We get a charge moving up and down. That charge makes the field change. But we now know that a changing electric field produces a changing magnetic field at right angles to it. And so there's a magnetic field. The electric field changes, the magnetic field changes. When the magnetic field changes, it produces an electric field, which produces a magnetic field, which produces an electric field, which produces a magnetic field, which produces an electric. This is why light can travel in space. There's no physical object moving. We've got a leapfrogging set of fields. Each one induces the other one. The rate at which the changing electric field produces a changing magnetic field and vice versa is what determines the speed of light. This was the huge breakthrough. When Maxwell worked that out and presented it to people, they were stunned that he had predicted the speed of light theoretically. They were measuring it, and in general, this is one of the big places where a theory gets rapid acceptance. When a theory can come in from the theoretical side with the same results that the experimenters have already presented. And so this is a tremendously useful understanding of the way nature works.